So we are moving into a slightly more complicated look at forces in Chapter 5. If you remember what we've been doing together, most of the things that we have done together have been in one dimension, right? The car is driving in this way, and it puts on its brakes, and it slows down, but it's all that one dimension, right? A ball falls from the sky, moving in the y dimension, right? And that works very nicely. Our math is fairly easy and fairly straightforward how we deal with that. When we add two dimensions, something that is moving not just straight up and down, or not just straight side to side, we have to add just a little bit more complicated math to it. And I will tell you, don't freak out. It's really the same kind of math you've done in the past. You've done trigonometry, right? Which is simply like using triangles and using sine and cosine and tangent. That's all this is being able to take something that is moving in both x and y and break it into its two pieces. And if you analyze the x movement, analyze the y movement, you've got the total movement present. Okay? So let's dive into that a little bit. Let's say I have a vector. Let's go review this one-dimension motion. If I have a vector that's 4 newtons, right? So I'm pushing this chair with 4 newtons of force, right? And Kieran comes up, and he pushes another 4 newtons of force. How much force is being put onto this chair? Pretty straightforward, right? Are you comfortable that we could visually, I could take, now let's see if this smartboard will work for me. I could visually take Kieran's force and put it right on top of my force. We call this tip to tail. These are vectors, right? We're putting the tail of his vector onto the tip of my red vector there. And that would produce a new vector, what we would call a resultant vector. And how long would that vector be? It'd be 8 newtons. Does that make sense? I'm telling you, this is the foundation of all we're doing in this chapter, is we're taking vectors and we're adding them together. The fun thing is they won't always be going in the same direction. Does that make sense? So this resultant would be 8 newtons. We're cool there? That's all right? Okay. So imagine now that instead of me pushing this chair directly in one dimension, okay, I push it in this dimension. So it's a little bit of both, right? That came off a little more sideways than I wanted. So instead of it being straightforward or straight to the side, it's going in both. Does that make sense? So if I were to draw that, let's say I would draw it something like this. Okay? Come on in, Matt. Did you want lunch? Okay. And let's say that again, I put on here, let's go with, it doesn't matter. Let's go with 5 newtons. That's the amount of force that I'm pushing. Are you comfortable that I can take this and I can break it into 2 pieces? That I'm pushing some that way and I'm pushing some this way? Does that make sense? That if I add these 2 pieces together, it gives me this motion. Like over here? I hear you. What I've just done is simply just put them together to make a triangle. You're correct. You could put this over there, the red on the left side, that would be fine. But I put them together to make a triangle, because we'll use that in the future. That's what I wanted to make sure you see. Yes, ma'am? Absolutely. You've seen this before, right? This is just a nice right triangle right here, right? Is there an equation you all know that we could find the length of that hypotenuse? Easy, right? Absolutely. Does that make sense? going on? Did you want lunch, Joyce?
Yes.
Okay. Sorry, just entering that into RenWeb. All right. So, if I step back for a moment, what I was describing was if I only had the blue one, we could find the green and the red, right? But are you comfortable that if I had a green and I had a red, let's change it up just for you, Gracia. How could I add these two together? Because they're going in two different dimensions, right? Go ahead. Okay. And again, what we're going to do is we're going to do this, what we call the vector when we add them, we go tip to tail. So I'm putting the tip of one with the tail of the other. That's why I drew that one on that side, Gracia. But you said, then what do I do then, Michelle? Absolutely. With the resultant piece, so we're putting them together tip to tail. And then this is just simply what we call the resultant. The blue one is just, if I take this plus this, it gives me the blue one. It doesn't have to be that way. No, you got it. So again, that is the resultant. Are you with me? And if I wanted to find that R, I would use that Pythagorean theorem you all just said, right? If I knew that this was 5 newtons and that this was 6 newtons, could I calculate and find the number for the resultant? We could, right? It would simply be a squared plus b squared equals c squared. If I solve this all out, it would be that c equals the square root of 5 squared plus 6 squared. Will someone pop that in for me? I'm just making this up, so I don't have an actual answer to give. But can you give me an answer quick? It does not. It's a good question. It does not. Someone got a number for me? Sorry? C is 61? Oh, please, yeah. The square root of 61 would be what? Can somebody tell me? I thought you were saying that C was 61. I was like, boy, that seems awfully large. It's close to 8. 7.8? Thank you. 7.8, and of course we'd say newtons. Now, we'd have to have said 0.0 and 0.0, so we actually don't have just one significant figure. Does that make sense? That's pretty straightforward. And that works really well if I have a 90-degree angle, right? If I have something going in a y, or an x, something going in a y, boom, Pythagorean's easy as pie, right? Easy as, that's a bad geometry joke. Wow, that was terrible. It wasn't meant to be. I'm subbing to Mr. Kaler in 4th period, so I'm already practicing. No, terrible, terrible. All right, but what if they aren't at 90 degrees? What if the two angles, what if somebody is pushing this way and somebody else is pushing that way? Can I use Pythagoreans then? No, because that only works with a 90-degree angle, right? So are there things that you have learned that you could use? Sorry? Sure. The law of sines or the law of cosines. And again, this is, sorry? Yes. So on page 123, they show you those two pieces. This is, again, 5.1 in your textbook. So if I was trying to put these to find this R, and I really should have moved that over. So we'll just extend this blue line just a little bit, just to make it a little better. If I wanted to find this R, right? And I don't, there are ways we can do this. So the law of sines, and this guy is looking at different ratios, right? That R divided by the sine of theta theta being the angle between these two guys, right? That is equal to A divided by the sine of A. Do you remember this at all? And I should change that to a little a. And then B equal the sine of B. And again, if you look at your diagram there on page 129, they show you, right, that B is here and A is there. A little geometry refresher for you, right? And this works well. And again, hear me when I say this here. It's best to use that law of sines, and this is taken right out of page 123, when you're given two angles and one vector. So if I know two of the angles and one of the vectors, law of sines is the best one to use. What this textbook's use most is the law of cosines. And that formula they give you there, again, also on page 123, that r squared is equal to a squared plus b squared, so just like Pythagoreans, right? But then you have to add minus 2ab cosine of theta. And we use this one. It's particularly useful when we're given two vectors and then the angle between them. And like I said, this textbook tends to use the law of cosines much more than the law of sines. Simply because they often will give you problems where one person's pushing one way, one's pushing another way, and they're at an angle to each other. Find the resultant. I guess it depends on what you decide to do with your lives. Some folks might use this more, some might use it not at all. But yeah, we seem to do more of having the vectors more than the angles.
Wait, so how would you use the first one? Like an example?
An example would be one vector with two different angles in that triangle. I don't have a good example to give you to go along with that. But again, this lends it more to the story problems that we do more in physics. So not that you'll never use this, but this is just much more common. Are you with me, my friends? So it means the same number you had for A, right? The same number you had for B. I'm multiplying them by 2, multiplying it by the cosine of the angle you were given, and all that is a negative number. It's being subtracted from the pieces here. The angle would be given, yeah. So you'd have to actually do the cosine first, right? So this would, again, think about order of operations, friends, right? This goes way back to Algebra 1. If you've got things that are multiplying and things that are adding, which do you do first? We multiply. So I'd have to multiply these guys all out. Find the cosine of theta, multiply it times A, multiply it times B, multiply it by 2, and then do your addition and subtraction. Of course, square those guys first, because squaring even comes before multiplication, right? Please excuse my dear Aunt Sally. Whew, man, old school. Right? That's what, I mean, physics, you get this, oh, it's all freaky. No, it's just the same math you've learned before. It's just twisting it in a little different way. Absolutely. Yep, absolutely. So, and again, are you comfortable that these are for when you have vectors that are not at 90 degrees? Does that make sense? Now, truthfully, you could plop in a 90 degrees here, and all this would just equal 1. It would be fine. Does that make sense? So this is really if you have 90 degrees between the two vectors, which we'll use this a whole bunch in just the next piece we're going to do together with this. But this is in case they aren't at 90 degrees. So let's look over at example problem number 1. That's there on page 124. I'm sorry? we will use a tangent formula to find the theta, to find the angle if we're not given that, but I'm going to hold off on that. And this little piece, we're not going to use it right now. Okay, so here's our problem. We have a 15-kilometer displacement and a 25-kilometer displacement when the angle between them is 90, and then also when the angle between them is 135. So this is two separate problems, right? So which one do you want to be A? Does it matter? Doesn't. Okay, that's the key. I want to make sure. It doesn't matter which, but just keep whatever you pick as A has to stay A, right? So let's say A is 15 kilometers and B is 25. Yeah, 25 kilometers. What's our angle? Okay, 90 degrees is the first one, and then we'll do another one that says theta is 135. Okay, and what am I trying to find? I'm trying to find the resultant. And you know that because it says find the magnitude of the sum, right? Add them together. That's what we mean by sum, right? And find out what that number is. Okay. Okay, so let's start with a 90. What formula would I use in order to do this? Pause. Let me draw it first. Are you comfortable that we're going to have, how about let's have A, B, X? Is that all right with you? It doesn't really matter. So this is 15 kilometers. And this is 25 kilometers. Right? We have a 90-degree angle here, even though I didn't draw it very beautifully. And I'm trying to find my R, which would be where? The hypotenuse, the connection between these guys. Right? Cool. Okay, so the formula I would use was what again? Sorry. I would use Pythagoreans. Right? So I'm simply going to plug them in. That R equals the square root of 15 squared plus 25 squared. Are you comfortable that square root's what the most mistakes get made is you forget to square root it? That's the easy mistake to make with these guys. So Pop, give me an answer here if you would. 15 squared plus 25 squared, and then take the square root of that. Okay, did it give you exactly 29? Okay, 29.15. How many significant figures should we have here? Just two, right? Yeah, absolutely. So therefore 29, and my units would be kilometers. Make sense? I'm going to try and slide this guy over here. Whoa, wow, that was exciting. You got it. Because the two vectors they gave us are at a right angle, so that's the easiest one to use. Again, you could use the other ones, but it was just going to give you the same answer. And the math is certainly less complicated. Okay, how about for the 135? Which, am I going to use law of sines or law of cosines? How do you know? I have two vectors and one angle, right? So therefore, that's when we talked about when we put these guys up here. Sines is for two angles and a vector. Law of cosines is two vectors and an angle. And you see that, right? Because you've got two unknowns here and one angle, right? And up here, I've got all of my angles there. So if I only know the angles, you're going to have to use the law of sines. All right, so law of cosines tells me, it's okay.
How would you know that it's not? Oh, wait.
You got it. All right, so here's our formula then, right? R is equal to the square root of 15 squared plus 25 squared minus 2 times 15 times 25, sorry, I'm running out of room, cosine 135. Now, there's one key thing you have to make sure on your calculator when you do this. What's that? Make sure it's in the right mode. What mode does your calculator need to be in? Degrees, right? If you're in radians, you're going to get the wrong answer. Y'all with me? Because radians are a way that you can measure a circle, but we're not using radians, we're using degrees. So you have to make sure that you're in the right mode. So pop it in. And again, remember that you have to do these first, right? Square it, multiply it. Let's see what you get. Yeah, cosine of 135, yep. Yep, 2 times 15 times 25 times the cosine of 135. You get that whole number. Somebody want to give me the intermediate step? What you would take 15 squared and 25 squared and multiplying those guys. 37.15 is what Mr. Ingetti, who I almost called your brother's name again. I apologize. 37.15? We good there? 37.15? Again, how many significant figures? Should be 2. So we'll round that to 37 kilometers. I'm going to see if I can't make this work. Nope, I can't. Are you comfortable that that makes sense? And again, it's always good to look at your answer and say, hey, does that make sense? Are you comfortable if I move this guy like this? And again, I realize I'm not perfect with my drawing. That this R has to be longer, right? This R has got to be longer if that's a larger angle. So it makes sense that that R should have a higher number. It should be bigger than just the Pythagorean one. Any questions here? Sir. With the iPhone, let me pull mine up just to make sure I don't tell you the wrong thing. You do have to go sideways. And then on the bottom left, there's a button that says rad. You don't want it to be on rad. You want it to be degrees. So if you push the rad button, it says rad up on top. You don't want that. You want the degrees. And you have to put the angle in first. So 135, then you push the cosine button, and it gives you the number. Right. Okay, so I'm sure you can guess what I'm going to ask you to do. On page 124, I'd love you to do numbers 1 through 4 for tomorrow, please. Again, if you're uncomfortable with how to do your calculator for these, please ask, and I'll be glad to lend my assistance if I can. 1 second here.